Hello, my name is John Ryan, and this is assignment 2 for Comp 361 Introduction to Robotics, Graph-Based Path Planning. So for path planning, we have a driverless car, and it's been given a graph, a directed graph that shows the road network where nodes are representing different cities, edges are the roadways, and their weights, costs, or the distance in miles. So I have to use the grassfire algorithm and determine the optimum path from the start node. So the key idea for the grassfire algorithm is that it ignores edge weights and finds the path with the fewest number of edges, so hops. So because this is a directed graph, we're going to start with our destination, and then we're basically going to flip the arrow and go back following that path. So we mark our goal as 0, and then we see that there's an arrow pointing into it. That becomes 1, an arrow pointing into it. That becomes 2, an arrow pointing into it. That becomes 3. There's 2 different arrows pointing into it. Those become 4. And then now we have the shortest path for start. Also note that these paths, if you go down here, you end up in an infinite loop. And if you go here or here, you end up here. So neither of these paths can ever result to the goal. So the shortest path is from the start to E to R to F to the goal. Now use Dijkstra's algorithm and find all the shortest paths from the start node to the goal node. So Dijkstra's algorithm visits the cheapest unvisited node and updates all fringe node costs. If the fringe cost is not smaller than a previously recorded cost for that node, it will remain the same. So it's tentative. All right, so I'll do a little example here. So we're going to start at the start here. So we'll make this red, so that's been visited. And we're going to look at its fringes, so what's directly connected to it. So we have P, which will cost 1. We have D, which will cost 3. And we have E, which will cost 9. So now we're going to visit the smallest cost unvisited node, which would be P, because it's 1. So now this is visited. And we're going to look at what it's connected to. So it's connected to Q, which will cost 16 because 15 plus 1. And now we're going to look at the smallest of all the fringes. So in this case, we have 3, 9, and 16. 3 is the cheapest, so we're going to visit this. We're going to look at its fringes. So we have 1, which would make this, that should be blue, sorry, 4. And then this one, which would be 11. And then also E here would get updated to be 5. So we're going to change this one, 5. And then we would look at the smallest one, that's 4. So we're going to visit B. We see that it's connected to A only, which would cost 6. We're going to visit the cheapest one. So that'd be 5. So we're going to go to E. Visit that. And then we're going to see that it's connected to R for 2 more, and then H for 8 more. And we're going to visit the smallest one, which would be the 6. Smallest unvisited. It's not connected to anything, so do it again. 7th is the next smallest one. Connected to F, which would cost 2 more, so that'd be 9. Then we're going to look at the smallest tentative one, B9, so we're going to visit that. See it's connected to C for 3 more, which would make this 12. That's bigger than that, so ignore that. And then to goal as well, which would be 11. And then that's our answer right there. The goal shortest path is 11 by following the path from start to D to E to F, sorry, to R to F to goal. So this is the answer that we basically just went through over here. So yeah, the shortest path was from start to D to E to R to F to goal, which was the total distance of 11. So explain the difference between the algorithms and their solutions for this given problem. So basically the grassfire algorithm just finds its path by expanding uniformly through the graph without considering the weights. Each edge is treated as having equal cost. The algorithm minimizes the number of edges from the start node to the goal node. And then in contrast, Dijkstra's algorithm explicitly used the weights of the edges to find the path that minimizes the total cost.